Hi, my name is Emmanuel Gallegos, and today I'm thrilled to be able to share with you my research into mobile head detection with thermal imaging for skin temperature analysis here at the Great Minds in STEM Conference in 2020. This work was done in conjunction with Professor Lynn Grew, as well as other students Shivali Chowdhury, Dikshant Jain, and Philip Aguilera from CSU East Bay and CSU Dominguez Hills. Before we get into the abstract, let me give you a little introduction into what our project is about. So our research focused on trying to build a tool to help combat COVID-19. So in the United States, there have been over 7 million cases of COVID-19, as well as over 200,000 COVID-19 related deaths as of September 30th, 2020. This is according to the European Center for Disease Prevention and Control. Now, COVID-19 has one giveaway in that fever is one of the most prevalent symptoms to manifest in people who have COVID-19. Not everyone, but it's a very common symptom. And so our research revolved around seeing if we could utilize that fact to create a system that could help users increase their situation awareness with respect to COVID-19. And what I mean by that is situation awareness refers to an individual using information about their environment or their situation to make a more informed decision. So if we could leverage a technology that could use infrared imaging to perform temperature analysis on people live, essentially we'd be developing a system that could help people increase their situation awareness by seeing or visualizing who around them might have a fever. And this kind of technology, getting into our background here, has actually existed for a while, particularly in response to the SARS outbreak of 2003. If you were around back then, you might remember that some of these systems were deployed at places like airports or government buildings. And the technology for these systems has evolved a bit since then, but the fundamentals are pretty much the same. Here we have an example here in figure 1, the guide IR236. You can see this system is on sale commercially for $12,000 US. And this unfortunately is par for the course for these kinds of systems, which range usually between about $5,000 or $30,000 for commercial grade systems. We wanted to see if we could take this kind of pre-existing technology that's already existed since the early 2000s, but bring it to a global user base. And to that end, we wanted to leverage a technology that is now becoming ubiquitous even in developing nations, which are smartphones. So if we could mount one of these types of systems on a smartphone that anybody could take around with them, we'd be developing a tool basically that could help most people increase their situation awareness, especially if they are like high-risk users who have maybe some sort of pre-existing condition, who are really looking to look out for themselves and look out for their families if maybe they live with someone who's high risk. So our fundamental hypothesis here is to use machine learning to perform object detection to localize heads from a smartphone live, and then perform temperature analysis on those head regions to inform the user if anyone has a fever. And looking here at our basic use case diagram in our hypothesis, we can see an example, and you can picture along. Imagine you're at a Costco, and you have a high-risk user who wants to check out, and they only are going on limited information about which line to go into. They might look at factors like if people are wearing masks, or maybe if anyone's exhibiting any obvious symptoms of COVID-19, like they're coughing excessively, for example. However, by giving them this tool, which we've dubbed the infrared fever indication system, they can then use their Android phone with one of these FLIR cameras attached to point their phone at these checkout lines, and an augmented reality type interface would draw bounding boxes around the head regions of all the individuals in the frame, and then inform the user if any of them have unusually high temperatures. And thus the user might see, oh, in checkout line 2, the clerk, as well as one of the customers, has an unusually high temperature. So they might avoid checkout line 2 and instead go to checkout line 1. And this is a fundamental example of situation awareness. So going back to our abstract now, looking at the system, we wanted to see if a neural network, a machine learning model that was small enough to run from an Android phone, could be trained on low resolution infrared images to detect human heads. And we're going to get into now the success that we found in doing this kind of analysis and how we did this research system, how we developed the system. So getting into materials and methods. Over here, we have an example of our machine learning models architecture. It's a bit complicated, but if you're interested in that kind of thing and into machine learning, you can, we can look into this. So getting into how this model was selected and how we got to this stage of even having this model available to us. So we decided to train our model in multiple stages. We thought that jumping straight from a general object detecting model to a low resolution infrared head detector model might be a bit too big of a gap. So we decided to do this training in 2 steps, and that allowed us also to have a mechanism for selecting a model to use. So we decided to do our training in the TensorFlow programming environment in Python. And the TensorFlow environment comes with a few object detection models that are available for use. These are cutting edge models that are constantly being developed and modified and improved. And so we selected 3 candidates that would be small enough to run from the Android platform to test. So to that end, and here in stage 1, we used the ADOS dataset, which is an open source infrared dataset of thermal images, to train our model to see which one of them would perform as the best object detector in infrared images. And we found with resounding success after analyzing our results that efficient det-D0 was the best model, and we would then use that model to proceed in stage 2. So in stage 2, we then retrained this model again that was initially trained on these moderate resolution infrared images, on these low resolution infrared images that we collected. So to that end, we, the research team, used FLIR 1 Pro cameras and went out into various places in public and collected a large data set of images of people for use in training our model to instead detect heads. This would be our fine-tuned model, which would then go on to eventually become a part of our infrared fever indication system. So after we had fine-tuned that model and performed a bit more analysis to make sure that it was robust enough for our uses, we then exported that model as a TF-Lite, TensorFlow Lite model, which is essentially a compressed version of the model which can run on the Android platform, where we integrated it into our COVID ID Android application. And so looking at the results of this process a little bit more deeply, here in stage 1, selecting a model, our stage 1 results, you can see what we have here are the 3 models that we tested out, along with some graphs describing their accuracy. What we have here are actually loss graphs, and this you can use loss to judge accuracy, as a low loss value means we have a high accuracy. So as these models were trained, as we fed these models images, we looked over time to see how their performance was doing. And what we want to see is this nice steady loss decrease that's converging to a low value over time. And for efficient det-D0, you can see we saw that for both of these kinds of losses. Classification loss being how well was it able to identify the things it was detecting, and localization loss being how well was it able to hone in on where those objects were within the image. So comparing this to our other models, CenterNet Hourglass, for example, didn't really converge, and the loss values were oscillating pretty wildly. Whereas looking at SSD MobileNet, we do see some kind of convergence coming out, but even still the values are significantly higher than what we are getting with efficient det-D0. So ultimately we went with efficient det-D0 as our middle stage infrared object detector. We then fine-tuned that model by retraining it on our personally collected data set of these low-resolution images, and we can see from the training we have these same curves which are also converging very nicely to very low values, low loss values, which again, excellent result. But of course we needed to perform more analysis once the model was actually trained. So to that end, we had initially split off 20% of our initial data to form a testing set. And so this was a randomly selected portion of our data, and we used that to see, once our model was trained, how good was it actually at detecting heads. And we found that the model performed with surprisingly high average precision and average recall, which are 2 of the primary metrics that are used to judge to judge object detecting models. So we achieved an average precision of 95.6%, which is very high when compared to, for example, Google's efficient det D0 model of 52.2% average precision. So 52.2, 95.6, significantly higher, though it's definitely worth noting that our model is only trained to detect objects from one class, which is a significantly easier problem than trying to detect objects from several classes, which is what Google was trying to do. That being said, our precision and recall were both robust enough, high enough values that we figured that our model was robust enough to continue on with stage 3 and then stage 4 of our development process. So stage 3 again was taking this model and compressing it so we could mount it onto our Android platform through our COVID ID application. And just to get a visualization of what these results really look like, here you can see some results from our stage 1 model. So up here, figure 9.1 and 9.2 show a couple examples of what a good inference looks like and what a bad inference looks like. So after we trained our model, we fed it some images just to see how it was doing, because we had our statistical analysis that told us pretty much all we needed to know. But just so we could see our results, we threw some images in there to see how it did. And you can see it was able to detect people fairly well. Looking back at our results, these values were converging, so we did have high accuracy. But here's an example of what it would look like when it did fail. You can see the person seems to, for some reason, look a bit darker than their surroundings, which might mean there was something odd about the temperature of the street that day, or perhaps there was a calibration issue, as thermal cameras tend to go through a pretty complex calibration process every so often, and it could have been this image was taken when the calibration was a bit off. Though that's just what we suspect was happening with an image like this. Figure 9.3 and 9.4, however, show our stage 2 model. This is the head detector model, as you can see. And even with an example of like a bad detection instance here, we can see the person is a bit farther in the background. They have sunglasses on, they might be wearing a mask. There are a lot of possible confounding variables that could be influencing why our model wasn't competent enough to say that there was a head here, because it would only draw this bounding box if it was significantly confident enough to say there was a head, according to a threshold that we set. And then looking here in figure 10, we see an example of our stage 3 model. This is actually the model from stage 2, compressed and mounted on the COVID ID Android application, which we're currently working on. You can see it performing a correct head detection on me as I was testing it out. This is only minutes after mounting the system onto the phone. And you might not be able to tell from this picture, but I was pretty excited about this result. This was an excellent result. And so I'm thrilled that my portion of this technology, at least, developing this infrared head detector, has been a success. And looking forward into this, what the real results are from our research. So this infrared fever indication system that I introduced in the beginning, could really present a new tool to help people increase their situation awareness and help them, improve their situation with regard to COVID-19 when they have to go out, particularly high-risk users or people who live with high-risk individuals. And the development of the head detector was very successful. We achieved very high average precision and high average recall, which is an excellent result given the low resolution infrared cameras that we used and the fact that our model is mounted on very low quality hardware, a $50 Android phone. The model has since been deployed on the COVID ID Android application. You can see our logo up here. And with the model fully trained, compressed, and integrated, now we can move forward with the thermal image analysis for temperature extraction. And we currently have a pretty simple method which just extracts the highest temperature from the image, though we're really looking forward to developing more robust ways of analyzing these thermograms. Now that we have this data, we can play around with what gives us the best results in trying to analyze potential fever cases, or at the very least, elevated temperature cases. And additionally, looking at this technology, this could serve as a proof of concept, not just for fever detection, because really what we were looking at with this research is, can you perform object detection with grayscale, low resolution images from the infrared spectrum on a smartphone? And from the literature review that I did prior to this research, I wasn't able to find any examples where this kind of technology was really being stretched to this high of a limit. There are head detectors that are mounted on smartphones. You know, Snapchat uses them, for example. They use face and facial feature recognition, but the cameras that they're using, the the RGB cameras that they're using are significantly higher in resolution. We're talking about 10 to hundreds of times higher in terms of their resolution than these low resolution cameras. So this technology could be used not only for fever indication, or even for the medical sector, but for other applications that could leverage, this technology for a low-cost system to perform temperature analysis with object detection in the infrared spectrum from a smartphone platform. Again, these systems usually cost tens of thousands, if not hundreds of thousands of dollars for military-grade systems. And what we're looking at here is a system that could cost hundreds of dollars instead. So looking forward, this research will hopefully also be used for future research into infrared thermography. Our research, looking back, was based in large part on the research done in 2003 with response to the SARS epidemic, right? So, we're hoping that even if this system, even if COVID, like a vaccine comes out before our system is developed, for example, this research could still be used as a base or as a proof of concept for future research to build off of. So we're thrilled with our results and really looking forward to doing our temperature analysis to see if we can get a system, going and launched that could actually help people. And thank you for joining me for this presentation, and I hope you enjoy the rest of your time at the Great Minds in STEM conference. Once again, my name is Emmanuel Gallegos. Have a good day.